Hi everyone, so in the last video we began to look at the Schwarzschild metric, which is the solution of the vacuum field equations for the gravitational field, so to speak, generated by a static, spherically symmetric mass. And we found, we didn't find it, but I simply stated that this is the answer. Okay, so this is the solution of Einstein's field equations in that case. And rather than writing it as components of the metric tensor, we tend to just write it in line element form. So ds squared is minus 1 minus 2gm over c squared r times c squared dt squared plus 1 minus 2gm over c squared r, that should be dr squared, plus r squared d theta squared plus r squared sine squared theta d phi squared. Here, theta and phi are just angles, okay, like spherical polar angles centered on your star that's generating the gravitational field. T is the coordinate time. R, now I sort of alluded to this in the last video and then I just kind of kept moving on. R here is not exactly the radius. So it's not exactly the distance from the center, okay, so your origin, you put your origin on your star, like the sun. It's not exactly the distance from there out to like the point in question. The reason being because of this factor in front. Okay, so this factor here actually gives you length contraction. What R actually denotes is if you have a point with this coordinate R, then it means it sits on the surface of a sphere with surface area 4 pi r squared. Okay, but that's not the same as saying that the radius of that sphere is r. Because why? Because we are in non-Euclidean space, and Euclidean geometry formulas don't always hold. So in this non-Euclidean space, if you have a sphere of surface area 4 pi r squared, the radius of that sphere is not actually r. Okay, so that formula doesn't hold anymore, and it's because of this factor in the metric that produces length contraction. But at any rate, that's just a small detail. But what we really want to focus on here now is motion of a planet in this metric. Okay, so for example, the Earth going around the Sun, or just a planet going around the Sun. Okay, m here will just be the mass of the Sun, but what is the trajectory of that planet? Okay, what does it look like? And remember what we said as part of the metric theory of gravitation. So the postulate of Einstein's theory of general relativity, one of the postulates is that motion under gravity, so motion in a gravitational field, is actually just free motion. Remember, gravity is not a force, according to Einstein. It's a fictitious force. So whenever you have a planet moving in a so-called gravitational field with no other forces, well, actually then it is just moving freely. Okay, the so-called gravitational field isn't a real force, so the Earth is just moving freely. And so in flat space, you would expect it to move in a straight line, but hey ho, we're not in flat space, because the presence of the Sun curves the space-time and makes it non-Euclidean. So in fact, the Earth follows the closest possible thing to a straight line in the curved space, which is a geodesic. Okay, and that's what the postulate of general relativity is. Particles moving in a gravitational field with no other forces, they follow geodesics. Okay, so what we want to think here is we want to find the path of, I'll say, a massive particle. Okay, so it just means a particle with mass itself, like the Earth. Okay. In this metric, in other words, in the curved space-time described by this metric. Okay, so the curved space-time produced by the Sun. We can also separately find what the path of a non-massive particle would be. Okay, so that would be like a photon. And in fact, photons are also affected by gravity. Okay, so in Newtonian mechanics, there was no mechanism that was explained for this. So we know that, like, if you have a ray of light, it will be bent in a gravitational field. Okay, it won't follow a straight path, and Newton's theory had no mechanism for that, but Einstein's theory of relativity will, but we'll see that afterwards. Okay, so first, for now, we'll just think about a massive particle, okay, like a planet or something, moving in this metric, okay? it follows a geodesic path. Okay, so how are we going to find the trajectory of the Earth? We have to take this metric and find the geodesic equations. Okay, so this goes back to what we talked about last chapter, and if you've forgotten that, maybe you want to go back to that video. I did do an example of finding geodesic coordinates from a metric. Okay, I did it in 2D elliptic coordinates. Now we're in 4 dimensions, so it's a little bit more work, but the steps are the same. So what's the first step in finding the geodesic coordinates? Okay, the first step is to find the Lagrangian. Okay, so what do? You take ds by du squared. Okay, so u here is just a parameter that's going to parameterize the path. Okay, so along the path of the Earth, you have 4 coordinates, okay? But along that path, each of the 4 coordinates will be a function of that single parameter u. Okay, but in fact, what we can do, and you'll see in a moment why this is helpful, but we can actually take this parameter to be the proper time. Okay, so if you remember what proper time is? It's like, imagine the Earth moving along its path and there's a clock on it, okay? The proper time is the time that's recorded by that clock, okay? So by a clock moving with the Earth. So you can just say at each point along the path, okay? So at each coordinate time and each r theta phi, as you move along the path, there corresponds a proper time on the clock on the Earth. So you can just use it as a parameter, okay? So in fact, rather than using just a general parameter u, we will use proper time. So I will actually say choose u to be tau, the proper time. And remember what our actual definition of proper time was. D tau squared is equal to minus ds squared over c squared. Okay, so you'll find that equation way back in your notes in special relativity, and it's still true here. So this is the definition of proper time. Okay, but we'll come back to that in a second. Let's just go with it for now. So this would just be ds by d tau squared. But anyway, finding the Lagrangian, you do it the same way as I explained in the example in the last chapter. Okay, so you will simply take your expression for ds squared. Okay, so just start with the line element ds squared, and everywhere you have a differential, a coordinate differential, so like dt or dr or d theta or d phi, you simply replace it by the coordinate with a dot. Okay, so you will have minus 1 minus 2 gm over c squared r, and then dt just becomes t dot, so this becomes c squared t dot squared, and then you have plus 1 minus 2 gm over c squared r, and then dr just becomes r dot, and then where are we? Yes, plus r squared d theta just becomes theta dot, and finally plus r squared sine squared theta not d phi squared, it becomes phi dot squared. Okay, there's our Lagrangian, okay, to find the geodesics. Okay, so how do we find them from the Lagrangian? We use the Euler-Lagrange equations. Okay, the Euler-Lagrange equations, which you need to memorize. You should memorize them, okay? And there are 4 of them, okay? 1 for each coordinate. So there's an Euler-Lagrange equation for t, an Euler-Lagrange equation for r, an Euler-Lagrange equation for theta, and an Euler-Lagrange equation for phi, okay? So let's look at each of them in turn. And okay, let's just do t first of all. So I'll just say EL, Euler-Lagrange equation for t. Okay, and what is it? It's d by du, okay, so the parameter of the geodesic goes here, but we'll just take that to be proper time, tau, now. Okay, so remember here, this dot, you know, the dot just means differentiation with respect to tau, you know, so t dot is just dt by d tau, and so on. Okay, so it's d by d tau the partial of L with respect to t dot minus the partial of L with respect to t equals 0. That's the Euler-Lagrange equation, okay, for the t coordinate. Okay, that general equation you should memorize, and be careful to get the dot in the right place, okay? It goes here, not here. Okay, and just let's work out the different bits. So let's say, therefore, let's just keep that d by d tau, and then in here, okay, open brackets, and then we'll put dl by dt dot here. So go down here. Where do we have a t dot? Just here. So dl by dt dot, you just take that power of 2 down in front. That's it. So you just have minus 2, and then 1 minus 2gm over c squared r times c squared t dot. Okay, so that's that bit, and then we have minus the partial of L with respect to t. Well, notice actually t itself doesn't appear anywhere. Okay, there's no t there, so that's just 0, and then this is equals 0. Now, in the next step, what you could do, although I won't, is you could now do this full differentiation with respect to tau. Okay, so do this full total derivative on here with respect to tau, but I actually don't need to do that, okay, because what have I got here? I've got, okay, so you've got a minus 0 there. Well, let's just rub that out. That doesn't do anything now. We don't need that. Look what you've got. You've got the total derivative of something equals 0. And if the derivative of something equals 0, total derivative of something equals 0, that just means your something is a constant. Yeah, so that just means whatever's inside this bracket is a constant. So we can just do that. So let's call everything inside here a constant. Let's actually, but we can leave out the minus 2, okay, because that's just constant. So we'll just say that 1 minus 2gm over c squared r. We don't need a c squared either. We can scrap that. That's also constant. So 1 minus 2gm over c squared r times t dot is equal to just constant. Let's just call it a. And that's it. Okay, so that's what we get from the Euler-Lagrange equation for t. Okay, what next? Get the Euler-Lagrange equations for the other coordinates. So the next one that comes up is r, but let me leave it for the time being. Okay, let me just come back to that after, and let me do theta and phi first. So let's do the EL, Euler-Lagrange equation for theta. So what will that be? d by d tau dl by d theta dot minus dl by d theta equals 0. Okay, and what will we have? So that's d by d tau. Okay, what's dl by d theta dot? Well, theta dot only appears here, so just take that power down. That becomes 2r squared theta dot minus dl by d theta. Where does theta itself appear? Just one place. Just there. You see that? Okay, don't miss it. There's a sine squared theta. So if you differentiate L with respect to theta, you're going to get 2r squared sine theta cos theta phi dot squared. Okay, and that's all going to be equal to 0. Okay, now in this case I can't do the trick I did up here. Okay, this time I don't have a total derivative equal to 0. I've got this extra term, so I am forced to just go ahead and do this full derivative. And remember, inside here I've got r squared and I've got theta dot. Both of those are functions of tau. Okay, remember, ultimately tau is the parameter of the geodesic. Everything's a function of tau. All of the coordinates and all of the dotted coordinates, they're all functions of tau. So I have to use product rule. So in the first term of product rule, let me just differentiate the theta dot and keep the r squared. So I'll have 2r squared theta double dot, and then in the second term, I'll differentiate the r squared with respect to tau. How can I do that? Chain rule. Differentiate it with respect to r first, and then multiply the answer by dr by d tau, which is just r dot. So that will be plus 4r dot theta dot, and then minus 2r squared sine theta cos theta phi dot squared equals 0. let me rearrange a bit. Let me just divide through everywhere by 2r squared so that I just have a coefficient of 1 in front of theta double dot. So theta double dot plus 2 over r dot theta dot minus sine theta cos theta phi dot squared equals 0. Okay, and that's the Euler-Lagrange equation. That's the geodesic equation actually for theta. Okay, so that's it fully written out. Okay, and we still need to do then phi and r. So let's do those next. Okay, so I've erased part of the board. I've kept the Lagrangian down here. So we need to do, let's do the Euler-Lagrange equation for phi next. And what we will get is as follows. So d by d tau, the partial of L with respect to phi dot minus the partial of L with respect to phi is equal to 0. And so we will have d by d tau. Okay, the partial of L with respect to phi dot. Where does phi dot appear? Just here. So we will have 2r squared sine squared theta phi dot. That's what you get if you differentiate that with respect to phi dot, just there. And then minus the L d phi. Well, phi itself doesn't actually appear anywhere, so that's just 0, and so this is equal to 0. And now look, I can do this trick again. So I can. So I have a total derivative of something equals 0, therefore the something is just constant. So 2r squared sine squared theta times phi dot is constant. Okay, but the 2 is just constant, so let me just scrap that. So just say r squared sine squared theta phi dot equals a constant, which I will call b. Okay, that's the Euler-Lagrange or geodesic equation for phi. So finally then, what about r? Why have I left that until now? Well, I didn't have to. I could go through the same steps for r, but it will be a bit messy because r appears in so many places, okay, basically. So it appears in a denominator here, and here, and here. Here's r squared, more r squared, and here's r dot. So it's going to be the messiest one if you do it that way. But handily enough, there's a shortcut for r. So rather than using the Euler-Lagrange equation for r, what we actually do is use the definition of proper time. So remember, we chose our parameter to be the proper time, and remember it's defined like this. So d tau squared is equal to minus ds squared over c squared. So in other words, what that tells you is that and remember that your Lagrangian, well, your Lagrangian is, okay, by definition, ds by d tau squared. Okay, so look at this equation here. If you rearrange it, you get, let me just go this way, you get ds by d tau all squared. So if you just divide this down here, it's equal to minus c squared. Okay, so what I'm saying is, if you choose your parameter of the geodesic to be the proper time, tau, then along the path of the geodesic, the Lagrangian itself will be equal to minus c squared. So for r, instead of using the Euler-Lagrange equation, what we instead use is that L is equal to minus c squared along the geodesic path. And what does that give us? So minus c squared is equal to all this. But let's plug in now the bits and pieces that we know, right? So we've got minus 1 minus 2gm over c squared r times c squared, right, t dot squared. What's that? Let's replace it now with this. Okay, so t dot is a divided by 1 minus 2gm over c squared r. So t dot squared will be a squared divided by 1 minus 2gm over c squared r squared. All right. And then we have plus the next term, which is just 1 minus 2gm over c squared r dot squared. And then we have plus r squared theta dot squared. Okay, let's just keep that as it is for the time being. So plus r squared theta dot squared. because we don't have a simple equation here for theta dot. We just have a differential equation for it. So let's maintain that the way it is. And then lastly, we have plus r squared sine squared theta phi dot squared. But we know what phi dot is from here. We can write it as b over r squared sine squared theta. So this will become b squared over r to the 4 sine to the 4 theta. Okay, and if we do some tidying up on that, then we just rub this out to make a little bit more space. We have minus c squared is equal to, right, what have we got here? That cancels that, so we just have minus c squared a squared divided by 1 minus 2gm over c squared r. And then we have plus 1 minus 2gm over c squared r dot squared plus r squared theta dot squared plus b squared over r squared sine squared theta. Okay, fine. Now I'm just gonna rub out this part. Okay, we have now already used the Euler-Lagrange equation for t, so we've put this in here, so we don't really need it anymore over here. So what we're going to do is, at this point, we're going to pick a particular value of theta for the planet to move in. Okay, so remember theta is like the polar angle. Okay, so you can choose initially theta equal to pi over 2. Okay, in other words, let's suppose that initially our planet, the Earth, let's say, moves initially, at least, in the plane theta equals pi over 2. That's the horizontal plane, that's the xy plane, okay? Remember, theta is measured from the z-axis down the way, so theta equals pi over 2 is the horizontal plane, equatorial plane. And actually, and suppose also initially that theta dot is equal to 0, so initially at least that first derivative of theta is 0, but then actually what will happen is that if you look at the geodesic equation for theta, you will find that initially if theta equals pi over 2, then cosine theta is 0 initially, so that's 0 initially, and initially theta dot is 0, so you get there from the geodesic equation that initially theta double dot is 0. And by further differentiation, if you were to differentiate that entire equation, again with respect to tau, and put in the initial conditions, you would find that theta triple dot would be 0. And in fact, all the higher derivatives of theta are initially 0. So, in fact, if the planet starts out in the plane theta equals pi over 2, it stays in the plane theta equals pi over 2. Okay, that's in classical mechanics. In the Newtonian problem, that also happens. So if the planet starts in one plane, it stays in that plane. That's a property of central forces. Okay. Now, that being the case, it simplifies things over here. Okay, because then this equation becomes minus c squared equals, it tells us what to do with theta dot, okay, and sine squared theta. So we will have minus c squared a squared over 1 minus 2gm over c squared r plus 1 minus 2gm over c squared r times r dot squared plus, okay, well theta dot is going to be 0. Okay, initially it's 0 and it stays 0, so that term is just gone. And over here then, we've got b squared over r squared sine squared theta, but theta remains at the value of pi over 2, and the sine of pi over 2 is just 1, so that just becomes b squared over r squared. And finally then, if I do just a little bit more rearranging, I can get my final or nearly final equation of motion for the particle. Okay, so I have just noticed that there should in fact be a power of -1 over there. Yeah, so that comes from the Schwarzschild metric. So that factor in front of dr squared in the metric has a superscript -1, so it should be there as well, and there as well. So now if I rearrange this entire equation, and look, this factor of 1 over 1 minus 2gm over c squared r, that's the same as that, so that bracket with a -1. So I can bring the, now let me see, I will bring the r dot squared on its own. So I want to have, I'll write it like this, so I'll bring this term to one side, so 1 minus 2gm over c squared r to the power of -1 r dot squared equals, so bring this term over here and you'll have minus c squared plus c squared a squared times 1 minus 2gm over c squared r to the -1. That's what that is. And then you'll have also minus b squared over r squared. And yes, and then if I divide through by this factor, in other words, multiply both sides by 1 minus 2gm over c squared r, I will have r dot squared is equal to, so I'll have c squared a squared, just from that term, and then these other two terms will give me minus c squared plus b squared over r squared times 1 minus 2gm over c squared r. And that, in fact, is the final answer for the equation of motion of the planet. Okay, so how do you, okay, so the planet moves in the plane, theta equals pi over 2. And then it has, right, what coordinates does it have? Okay, theta is fixed at pi over 2, and at each point there's a radial coordinate, or there's an r coordinate at least, so it satisfies this differential equation. Okay, so this r dot, remember, is just, this is just dr by d tau. Okay, squared, that's what r dot squared is. So tau is your parameter. So this is a differential equation for r in terms of the parameter tau, which can in principle be solved. And then from that, you can also get at any value of r, you can find phi. Okay, how do you get it? From here. Okay, so phi dot is a constant. So phi dot is just b over r squared, so that can be solved to get phi as well. Okay, fine, so that's actually the answer. So the path of the planet looks like this. It's described by these equations. Now, so what does it look like, right? Doesn't really tell us much. Well, what it's actually best to do is change your parameter. Okay, so at the minute we have an expression for r as a function of the proper time tau. Okay, so this is a differential equation for r in terms of proper time tau, and we have a differential equation for phi in terms of proper time tau. Fine, that's a solution, that's one way of writing it, but what we would actually prefer to do is to eliminate tau completely, and rather just express r as a function of phi. So we would prefer to have r as a function of phi. Okay, so let's imagine, you know, the Earth is moving along around the Sun, it's stuck in that plane, theta equals pi over 2, but as your angle phi, your azimuthal angle increases, what's the value of r at each angle? That would be a better way to parameterize the orbit and to visualize what its shape is going to look like. So how can we go about doing that? Well, let's think. Okay, so I've just erased one side of the board, but as I say, we want to change this so that r is parameterized in terms of phi. And the trick that we use here is not obvious, but it comes from the Newtonian theory of gravity, the Newtonian theory of orbits. And what we do is, in this equation, we introduce a new variable. So we introduce a new variable which I will call W, and it's just 1 over R. Or in other words, R is just 1 over W. Bit of a mess there. Okay, and then we're going to plug that into this equation and see what happens. Okay, so R dot, what's that? So we need R dot. That's just dr by d tau, but we can use the chain rule. So if we write R like this, so R is a function of W, we can just have instead dr by dw times dw by d tau. Chain rule. But actually, what we want at the end of the day is R as a function of phi. Okay, radius as a function of angle. So what we will actually even do is one more step. We will have dr dw, and then instead of dw d tau, we will use the chain rule on this one and just have this as dw d phi d tau. Okay, and actually we know what some of these pieces are. So dr by dw is, you can get from here. R is 1 over w, so dr dw is minus 1 over w squared. And then dw d phi, we don't know yet, but d phi by d tau we know, although unfortunately I've rubbed it out. But that's just phi dot. Okay, that's just equal to phi dot, that part. And that came from the geodesic equation for phi. That was actually just b over r squared. Okay, but b over r squared is just bw squared. So that w squared cancels that one, and you've just got that this is equal to minus b dw d phi. Okay, so r dot is just minus b dw d phi. And so using this transformation on here, it's not obvious where we're going with this, but just watch. Put this in here. So on the left hand side, you'll have b squared dw d phi squared is equal to c squared a squared. And now we will have minus c squared plus b squared w squared. Okay, 1 over r squared is just w squared times 1 minus 2gm over c squared times w. And in the next step, what we will do is just to multiply everything out here. So therefore, b squared dw d phi squared is c squared a squared. Right, so what have we got? We'll have minus c squared, and then we'll have minus b squared w squared. And then we will have minus c squared times minus 2gm over c squared w. So that's just plus 2gmw. And finally then we will have minus b squared w squared times minus 2gm over c squared w. So that's just going to be plus 2gm b squared over c squared w cubed, if I've done that right. Okay, and then in the next line, we can divide through by b squared. So just have then dw d phi squared is equal to c squared a squared over b squared minus c squared over b squared minus w squared plus 2gm over b squared w plus 2gm over c squared w cubed. Okay, and now what we're going to do, now this seems really crazy, right? It seems like we're not making this any simpler, but we're actually going to, we've got a differential equation here, okay, and it has now w as a function of phi, okay, which is pretty much what we want, okay? I said we want r as a function of phi, but if we can get w as a function of phi, that's good enough, because then r is just 1 over w. That's really easy, okay? So if you get w as a function of phi, then r is just 1 over w. So that's dead simple. And this differential equation, now this is a first order differential equation here. Okay, so you just have the first derivative of w with respect to phi, but it's impossible to solve. Okay, so it's totally impossible to solve it analytically. So we're going to do something that seems crazy, and we're going to take this differential equation and we're actually going to differentiate it all the way across, okay, with respect to phi, okay, with respect to phi. Why would you want to do that? Doesn't that makes it worse? Surely that makes it into a second order differential equation. Yes, true, it does, but actually it's an equation, a differential equation that we can handle more easily. So let's just go ahead and do that. So differentiate with respect to phi. Now, how do you differentiate this with respect to phi? Use the chain rule. So you've just got something squared. So just differentiate with respect to the something first. So you just get 2 times whatever's inside the bracket, and then multiply your answer by the derivative of the something with respect to phi. So it's the derivative of dw d phi with respect to phi. That's d2w d phi squared. So that's what happens on the left-hand side if you're differentiating with respect to phi. Okay, that's what we're doing here. Now, what happens over here? You've got c squared a squared over b squared. That's a constant, so it just vanishes. You've got minus c squared over b squared. It's gone, it's a constant. Now, minus w squared. Differentiate it with respect to phi. Use the chain rule. Minus 2w dw d phi. Plus 2gm over b squared. So that's just going to be plus 2gm over b squared dw by d phi. And then finally plus 6. Okay, so 3 times 2 is 6, gm over c squared, w squared, dw by d phi. And now what we can actually do is, we can cancel all the way across dw by d phi. So you just divide through by there, 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 there. And fine. And what we will also do now, well, we assumed there that dw by d phi is non-zero. Okay, so we assumed that w does have to vary with phi. It has to be dependent on phi. So that means the radius has to change. So this doesn't work for circular orbits. So we're just assuming there that the orbit is non-circular. But okay, and let's just rearrange very slightly, and we will bring this term over to this side. And we will also divide the whole thing through by 2. So therefore, we will get d2w by d phi squared plus w is equal to gm over b squared plus 3gm over c squared w squared. And that is our final equation of motion. Okay, so that is a differential equation, and yes, it's second order, but for w as a function of phi. Okay, and if you know w as a function of phi, then you can get r as a function of phi very easily. R is just 1 over w, and it's called the orbit equation. Okay, so maybe let me write it up here. Okay, so this is the orbit equation. Okay, and how do you solve it? That's the not so easy part. So how do you actually solve it to get w as a function of phi? Well, turns out, and again I show this in the lecture notes, the PDF, it turns out that in Newton's theory, you can get the exact same equation. Okay, so in the Newtonian theory of gravity, you get the exact same equation, except without this term. Okay, so the Newtonian orbit equation is the same thing, so d2w by d phi squared plus w equals gm over b squared, some constant squared. So it's the same thing, okay? And in fact, this is an equation that you know how to solve. okay, in principle. It can be solved exactly, okay, so it's a second order linear differential equation with constant coefficients, okay? So you can use it, you can solve it using the auxiliary equation and complementary function method that you would have seen in first year, okay, level 1 applied maths. So it's a second order linear differential equation with constant coefficients. You solve it by solving the auxiliary equation to get the complementary function, okay, so you get the complementary function from the auxiliary equation, and then you find the particular integral. Okay, at any rate, the solution ends up being as follows. And rather than w, I'll just now change back to r. So you get r of phi equals something like this. So p over 1 plus e cosine phi. It has that form. Okay, so here p and e are constants. And this is actually the equation of a conic section. Okay, E is the eccentricity of the conic section. So if E is less than 1, you get an ellipse. If E equals 1, you get a parabola, which is an unbound orbit. If E is greater than 1, you get a hyperbola. So for the example of like the orbit of a closed orbit of a planet, then in Newtonian theory, E would be less than 1. Okay, so you get an ellipse. Now, fine, but what about general relativity? Well, I don't want to go into the full details here of how you solve this equation. Again, it's something that's a little bit too tricky and a little bit too time consuming to be asked on exam, but the full details are in your lecture notes. What you essentially do is, to solve this equation with this extra term now, due to general relativity, you take w, or you assume that the unknown function w can be written as the Newtonian w, okay, so this thing plus a small correction. So it's like we assume that Newtonian gravity is almost right, okay, so the orbit will almost look like this conic section, but with a small correction. So you take this and then plus an extra correction, and by substituting it in here, then you get a differential equation for the correction. Okay, which you can solve at least approximately. So the Schwarzschild orbit equation, so the solution, I'll simply state it here, of the Schwarzschild orbit equation is, and I'm just going to copy it from this page where I wrote it down earlier, just to make sure I write it correctly. So it's r of phi is equal to p divided by 1 plus e cosine 1 minus epsilon times phi, where epsilon is equal to 3 g squared m squared divided by c squared b squared. Okay? So you see, it looks almost the same, okay? And in fact, the only difference is here, you've got this, instead of just cosine phi, you've got cosine 1 minus epsilon times phi. And this epsilon, you know, this is a small number, okay? So it's really small, because look, it's got c squared in the denominator. So yes, it is a small change from the Newtonian orbit, but still it is a change. And if you look here, go back to the Newtonian solution a second, okay? So this leads on to the idea of precession. And again, this, okay, the phi dependence here is just through cosine phi. And what's the period of the cosine function? It's 2 pi, okay? So as phi goes from 0 to 2 pi to 4 pi, this function is periodic, okay? So let me just draw it over here. Okay, so the Newtonian orbit equation is periodic in 2 pi, okay, as I say. So as the angle phi goes from 0 to 2 pi and from 2 pi to 4 pi, cosine is periodic, so you keep coming back to the same value of r. And let's just say, for the sake of argument, that e is less than 1, so it is an elliptical closed orbit. So say this could be like the sun here at the origin of coordinates. And then you have the Earth. Okay, well, let's put it actually on up. So imagine here's your Earth here. And it's following an elliptical path. Okay, so the sun is at one of the 2 foci of that ellipse. Okay, in fact, that's where the word focus comes from. It's Latin for fireplace. There you go. So the Earth goes around this elliptical orbit, okay? So the angle phi is just measured here, okay? It's that azimuthal angle. So as phi starts, you know, if it starts here and then goes through a full 2 pi, the Earth comes back to the exact same place. And again, phi goes on to 4 pi and to 6 pi and so on and so on. And so you just get a closed ellipse, and the planet will remain in that ellipse forever. Okay, so if there were no other forces at all, this would continue forever, unchanged. But in general relativity, in the Schwarzschild metric, it's slightly different. Okay, so the Schwarzschild solution, let's think about that. So again, here's the Sun, and here's our xy coordinates, or xy axes. Now, this here function is not quite periodic in 2 pi. Okay, not quite periodic, okay, in 2 pi. So, what actually is the period of this function? Okay, well, let's think. Okay, so cosine of whatever will come back to the same values when the whatever is equal to 0, and then the whatever is equal to 2 pi, and the whatever is equal to 4 pi. So it's whenever the argument of the cosine is equal to a multiple of 2 pi. That's when you keep getting back to the same values of r. So let me just do this as a little aside. So if you have 1 minus epsilon phi equal to some integer multiple of 2 pi. Okay, so you can just start from 0. Okay, so n equals 0, 1, 2, 3, and so on. So what values does that give for phi? Let's see. So phi will just be 2 pi n divided by 1 minus epsilon. Okay, but remember that we said epsilon was small. Okay, look, it's got c squared in the denominator. So you can actually, let me just write this as 2 pi n 1 minus epsilon to the minus 1. So you can actually use the binomial theorem on this to first order to say that this is approximately 2 pi n times 1 plus epsilon. And so epsilon here, yes, is 3g squared m squared over c squared b squared. And so the period is 2 pi times 1 plus epsilon. Okay, so not just 2 pi anymore, but 2 pi times 1 plus epsilon. So 2 pi, period is equal to 2 pi, sorry about that, 2 pi times 1 plus 3g squared m squared over c squared b squared. So in fact, if I just multiply that out, it's 2 pi plus 6g squared m squared pi over c squared b squared. Okay, so the angle phi has to change by this much. Okay, so to bring r back to the same value. Okay, so it doesn't have to just go from 0 to 2 pi, or from 2 pi to 4 pi. It has to go from 0 to this much, and then from this much to 2 times this much to get r back to the same place. Okay, so imagine that your Earth starts out here, just, okay, and it comes round, but as we get around to here, we don't get back to the same value of r here, we actually get it a little bit further on. Okay, so that little angle there is this extra bit. This is the 6g squared m squared pi over c squared b squared. And then when it goes around another time, you get back to a little bit even further to the same value of r. Okay, so this is plus another 6g squared m squared pi over c squared b squared, and so on and so on. And so your orbit, it looks almost like an ellipse, but over time, this ellipse appears to rotate. Okay, so it's not really an ellipse at all. It's actually not even really a closed orbit. Okay, it keeps just going round and round like this. So it looks almost like an ellipse, almost like a closed ellipse, but not quite. It's like this ellipse just keeps rotating, and that is called precession. of orbits. This was one of the first things that led people to know there was something wrong with Newtonian gravity, actually. So Mercury, the closest planet to the Sun, its orbit was observed to precess. And so in the next video, now that we've done all this, I'm going to show you a little video demo of this precession, what it looks like. Now, I appreciate this video has been very long. Okay, very long. What have we done? Let's just go over it verbally again. We took the Schwarzschild metric, we found the Lagrangian, then we tried to find the equations of motion of a particle, okay? They will be geodesic equations. So we find the geodesic equations in that metric for the t-coordinate, for the theta coordinate, for the phi coordinate. We didn't do it for the r coordinate. We could have, but we didn't. We instead used the fact that L, the Lagrangian, is equal to minus c squared along the path of the particle, if you choose the parameter of the geodesic to be the proper time. And then we assumed that the particle will be restricted to the plane theta equals pi over 2. Or in fact, we showed that if it starts in the plane theta equals pi over 2, it stays there forever. And then we found a differential equation for r, the r coordinate as a function of the proper time tau, and a differential equation for the phi coordinate as a function of tau. But we didn't want that. Okay, so that was a solution, that was the answer, but we would rather have r as a function of phi. We would rather eliminate tau, and we did that by finding the orbit equation. So we introduced a new variable, w equals 1 over r, we find the orbit equation, and we're saying, I'm just stating this is the solution, okay? And it leads to this precession of planetary orbits, because it's not quite periodic in 2 pi anymore. So, long video, but very important and very, very typical of exam type questions, okay? So you could well be, if you had an exam question on general relativity, you could be given the Schwarzschild metric, or perhaps the Schwarzschild metric maybe with a slightly different notation than I've used here, or maybe a slightly different metric that describes a slightly different situation, a slightly different distribution of mass rather than a spherically symmetric, non-rotating star. But at any rate, a very typical thing would be to be given that metric and to find the geodesic equations, the equations of motion, find the orbit equation. So well worth looking through this again.